Hi, I'm Stephen Nesherba, and I'm here to help you out with this idea of the principle of corresponding states. So the real essence of, well, the conceptual essence of it is that all substances look kind of similar around the critical point. So there's the critical point of this gas, and here it's supercritical, and here we have the two-phase region of liquid and gas. So that's one important concept, and the quantitative part of it goes something like this. We have defined this thing called a reduced temperature. The reduced temperature is the actual temperature divided by the critical temperature, and I've just rearranged that equation there. But also the reduced volume is the actual volume divided by the critical volume, and so forth. So obviously, if I made a graph of an indicator diagram for a substance in reduced variables, then the critical point will occur at a reduced pressure of 1, reduced volume of 1, and as I've labeled it here, a reduced temperature of 1. So, okay, and again, the whole idea of principle of corresponding states is that all substances more or less line up this way. So, just to kind of take a quantitative example along those lines, let's just suppose that we had carbon dioxide, and it had a reduced volume of 1.5. That means the volume was 50% bigger than the critical volume. And let's suppose it was a little bit hotter than the critical temperature. Let's say its reduced temperature was 1.04. That means it's 4% hotter than the critical temperature. And so that's going to show up on this graph as something like this. Okay. That means that, for example, the reduced pressure must be 1.05. Okay, what are the actual temperatures, volumes, and pressures associated with that point? Well, let's see. I can just use this equation right here. The actual temperature would have to be the reduced temperature, 1.04, times the critical temperature of CO2, which I've written up there, 304. In other words, the actual temperature must be about 4% bigger than 304 Kelvin, which turns out to be 316 degrees Kelvin. And so on for the other variables. They would all scale up appropriately according to these critical constants. What if we were actually looking at water? And I was interested in the same point in this relative, in the reduced graph. Well, now I would say the actual temperature would be the reduced temperature, 1.04 again, but now we would multiply it by the critical temperature of water, 640 Kelvin, to produce an actual temperature of 673 Kelvin, 4% higher than the critical temperature. And once again, same with the other variables. Okay.